So, in 15.2, we're going to talk about line integrals. And so I'm going to use this nice piece of paper to demonstrate what's going on. What's the area of this piece of paper? Width times length, so 8.5 by times 11. You know the length of the piece of paper, doesn't matter. Okay. What's the area if I curve it around like this? It's exactly the same, right? Nothing changes. And so that's all a line integral is. It's you have some line in space or on the plane, right? And then you have some function sitting up above it, and you want to calculate essentially the area of the curve above that line. Does that make sense? And so you can think about what we did in. Oh, I thought that would rip in a cool way, but it's not ripping in a cool way at all. There. If you can think about something like this, right? So here's your function. So how would we have calculated the integral in calculus? We would have taken here to here. We would have said that's AB, right? Oh, A to B. And then we would have integrated our function f of x, and so the area would be the integral from A to B of f of x dx, right? And so now, what if instead of being flat, your curve does the same thing, but it's all swirly now? So now, let me just think of it this way. Here's xy, and then you got some curve in there, but essentially your curve does the same thing, right? It follows that guy, but it's getting lower. Let me just exaggerate it. Okay, and so the idea is, right, I'm getting really low there. Function is Does that make sense? So you got that curve like that. And so, so it's not enough just to figure out where it moves in the x or y direction, right? It doesn't go from A to B, but you can think about doing the same thing. How did we first approximate this area back in calculus? We said the approximate area between one slice was xi plus 1. We just said we'll take the height of the function, right? And then we'll multiply it by the width. And so what's the height of the function? Well, f of one of these guys, and what's the width of that rectangle? That was delta x, right? And so we're going to play the same game here. We're going to break this line up into a bunch of little pieces, okay? And so the sort of approximate area on each slice will be, so now this is a function of not just x, but x and y, right? It's snaking through space there. And so it'll be, I'll call it x sub y and y sub I still, like some points that break up this thing. And then we multiply by the distance, but that distance isn't delta x or delta y, it's actually delta s, where s was arc length, remember? This was your arc length. And we'll come back to that formula in a second. But the point is, then you take limits, and this area turns into the integral from A to B of your function dx. Okay? Take a limit here. Limit. And this becomes what we call the line integral. Okay? And so let's call this C as this curve. Okay? And we'll call this thing the integral along C of f of xy. Well, let me write it. Yeah, I guess I'll write it. F of xy ds. Okay? And so, how do I want to say this? So, suppose your C is defined by some r of t where t ranges from A to B. Okay? So again, that's some vector valued function giving you your curve, right? And then you want to take the integral along this curve. The curve is now defined by this guy. well, this becomes the integral from a to b, and you just plug that r of t into your function, okay? And ds still. And then if you remember, what was ds? That's the derivative of arc length. Arc length was the magnitude of r prime, right? And so this becomes the integral from a to b, f of r t times the magnitude of r prime of t dt. And so there's sort of our, I don't know, I'll say generic arc length formula. So the arc length formula we use for basic examples, right? And things will get messier as we move along. And we'll have to come up with some other approaches to calculate a line integral. But this is the line integral over that curve of this. So take the definition basically as this for now. Okay? So I'll write it. So again, the full definition is really the whole, right? Approximate it and then take limits. But in practice, we use this as our working definition for now. So let's try an example. So let's do example, find the integral over the curve of 2x plus x squared y ds, where c is the upper half of the unit circle. Okay. All right, so this requires us to remember some stuff, which I don't know, is good. It's coming back to stuff you've seen before, but as we get older, our memories fail us. Okay, so upper half of the unit circle, circle of radius 1. Now, all you need to do is find one parameterization of this. There's all kinds of different ways you could parameterize the unit circle. I think 99% of the time the easiest way is to use the sine and cosine parameterizations that we've seen before. And so if you remember, right, if you, let me just plug this in. Sine, cosine, remember if we do that, that's the unit circle, right? Sine and cosine. Does that give us the right parameterization? It could if we changed our bounds. Maybe we'll do that. Where does sine of t, cosine of t, where does that start? 0, 1, right? 0, 1. So it would start up here. And so I suppose you could do that, but you'd have to, you want it to do, and it goes this way, right? And so you'd have to get over to here. And so that would be when t is, so pi over 2, pi, 3 pi over 2, right? So you have to go, t could go from 3 pi over 2 to 5 pi over 2, right? Another pi. You could do that. That would be one way to parameterize it, but I think it's easier just to do this parameterization. Cosine of t, sine of t, and so if I want just the top half of the circle, I just started giving it to you, but where does the t have to range from? 0 to pi. Does that make sense? So you're going to see things like this over and over again. It's if it was the right half of the circle, then that sine cosine would have been the right choice to make, right? You can always adjust your thetas, but it's easier just to pick something nice and get a nice set of bounds so you don't have to worry about 5 pi over 2 floating around in your problem. Okay, so now let's just, I'm going to leave this formula up here. We're just going to follow this formula. Right, so the integral over that curve of our function ds is the integral from a to b, so from 0 to pi, f of, and so maybe this is notation we haven't used before, but when you take f of the vector, it just means this goes in for x, right? That goes in for y. So you're just doing f of cosine sine, right? And then what's r prime? Right, like it'll be negative sine cosine, right? And then that magnitude will be 1. That make sense? So you get that. T. All right, so now let's plug these things in. So here's our actual function. Right, 2 plus x squared y. So when we plug those in, I forget what was there. We get what? The integral from 0 to pi, 2 plus, and then x squared, so cosine squared, t times y, sine of t times, and again, I'll just write it up, cosine, sine squared plus cosine squared, right? That's all just 1. And so go ahead and integrate. What do you get here? 2t 0 and pi. And let's just take our time. Cosine squared of t sine of t dt. So in order to integrate that, what do we have to do? Or what do we have to do? Substitution, right? U equals cosine. What's du then? Negative sine. You can change your bounds if you like. This gives us 2 pi here. We end up with negative u squared du then, right? And what do our bounds become? We plug 0 in for t. 1 and then negative 1, right? Okay, and then just go ahead and integrate. So this is 2 pi plus, so plus negative u cubed over 3 1/3 minus a negative 1/3, so is that okay? Let's well, let's leave that first. All right. So let's do this one. So find the integral c over c of 2x, where c consists of c1, which is y equals x squared from 0, 0 to 1, 1, followed by c2, which is the line from 1, 1 to so all we're doing is we're following the parabola from the origin, right, up to 1, 1. There's the first part of the line, and then we just, I'm going straight up. That wasn't what I thought I had done. Okay, we'll do that. Does that make sense? So follow the parabola, and then we go from 1, 1 straight up to 1, 2. Right. Y equals x squared, so that's your parabola from 0, 0 to 1, 1.
Yep.
And then followed by C2, and it's the line from 1, 1 to 1, 2. So it's
Okay.
that straight piece of line. Is that okay? I have no recollection of ever doing this problem. So must have put it in my notes for some reason. Anyways, we get this as our C2. Does that make sense? All right. So I haven't written any of these rules down, but hopefully it's pretty clear. If your C, your full curve, is broken up into two pieces, the integral over the full curve can be obtained by doing what? What would you guess? The integral over the first part of the curve, right, plus the integral over the second part of the curve. That seem reasonable, everybody? And so it's just 2x ds. Okay? And so the point is that on each piece of this curve, we'll have a different parameterization that we'll use. Okay? So whenever you're just given a function, so let's just break these down one by one. So C1 can be just obtained like this, right? You just let t be x every time, and then your f of x is your y. So it follows t and then t squared. And then where do the t's go from in this one? 0 to 1. Is that okay? That'll bring you along that piece of that parabola from 0 to 1. How about a parameterization for C2? So what's your x value every time? It just stays 1, right? And then your y value, you could call it t, and then if you call that t, then where does it go from? From 1 to 2, right? If you call it t, because you're starting up at 1, 1, 1 to 2. Does that make sense? You could have called it t plus 1 and went 0 to 1 or any other variant of that one. So it won't make a difference. So now let's just start filling these things in. So this first one, right, becomes the integral from 0 to 1. 2x is what? 2t. And then, well, let me just write it out again. Magnitude of r prime, right, dt. So what's the magnitude of, or what is r prime actually?
2.
So 2t, we'll do the magnitude of 1. Okay? And then dt plus, we still have the integral along the second piece of the curve, right? Perfectly smooth today. So that's from 1 to 2, right? And then what's 2x in this case?
2.
Just 2 times 1, right? And then what's your, well, I'll do it again, magnitude of r prime, dt, and so this time 1 to 2, 2, what's r prime? 0, 1, right? The derivative of that stuff. Does that make sense? And then you just work your way through. So this first one gives us the integral from 0 to 1 of 2t square root of 1 plus 4t squared, right? dt. And then the second one will be nice and easy, just 2, right? Does that make sense? Okay. So what do you get here then? Could do a u substitution if you have to, right? 1 plus 4t squared du is 8t dt. Our bounds shift then from 1 to...
Just 1/4 from the square off.
Oh, no, yeah, that's, so you're saying 1/4, where do you, no, that's fine. And then the bounds are what now?
1 to 17?
1 to 17?
Yep.
Yep, I think that's okay. 2 squared, so 4 times 4. That make sense? What's this one give us? Just 2, I'll just write it. 2t and then 1 to 2, right? So it'll be just 2. And then this one, integrate the square root. So I'll just do it. U to the 3/2 over 3/2. Again, probably comfortable enough to clean that up on the first pass. 2, and so yeah, 1/6, right? End up with 1/6, and then what? 17 to the 3/2 minus 1, which isn't anything particularly nice, and then plus. Is that okay? Yeah.
Shouldn't we have the squiggle fork over there?
Where are we at? Here?
Yeah,
Square root of,
one,
right, but what's the square root of 1? It's just 1.
yeah.
So that's okay. Ask about anything you think looks weird. We've all done that exact same thing. We're like, oh, that should be in there, and it turns out to be something obvious. Okay. So, let's see. Definitely don't want to get into the line integrals over vector fields yet. Well, let's stop here for right now.